bring our next presenter up on stage, but first I'd like to say a few words about him. Jules is a freelance consultant specializing in safety-critical systems, mathematical software, and compilers and languages. He has been writing, teaching, and speaking for 25 years and conducts frequent lectures and workshops. He is the author of Extreme Reliability Programming Like Your Life Depends on It, and the originator of problem space analysis. He lives in northeast Scotland, so he knows a few things about Scotch, I imagine. Jules, welcome on stage.
Thank you.
Thank you. Listen, before I let you get started with your presentation, one quick question.
Sure.
Craft Hub has been alive and kicking for 10 years now, and we've grown exponentially. And the IT world is growing even faster exponentially than that. Just a quick question for you. What advice would you give people starting in the IT field today, be that programmers, system engineers, or any other type of thing there? What advice from all your experience would you give somebody?
I think the biggest advice I could offer is when you're starting out, what you see is technologies, languages, new platforms, these sorts of things. But these don't last. They have a half-life of 5 years. And unless you're really lucky, you're going to pick the wrong one. So it's much more important to learn about the basics. It's much more important to learn the computer science, learn the mathematical foundations. These things are universal. They will last for your entire career. The technologies come and go. The fundamentals stay the same. So stick with that. We are all programmers, aren't we? So can we be honest with each other here in the privacy of this tent? We actually have a terrible reputation. Sorry, I've just realized I haven't got any of my cues, so I'm really shooting from the hip now. Software is a byword for blown budgets. It's a byword for missed deadlines. A lot of the time, software delivers, it disappoints when it delivers. But basically, people don't like working with software because it feels brittle, it feels unstable, and we take on that reputation. Seen from the outside, we're not actually very good at our jobs. And the trouble is that everything that we've been talking about throughout this conference has been all about stuff which is built on top of code. None of this stuff makes sense unless we can write the code to support it. And it's a problem if we can't produce reliable code. Okay. And yet, despite the problems that we've been having, the aircraft that I came here on is flown almost entirely by software. We have hospitals full of life support machines whose job it is to keep people alive. And our crowning glory, the internet, we have built an entire global communication system which is resilient enough to be able to base our entire emergency responses on. So the proof is, what this is demonstrating, is that when it comes to it, when we really have to, we can build, industrially, we can build software that we can trust our lives to. Why is it that most of us don't? That's what's interesting to me. I am a consultant. And that means I've seen the inside of an awful lot of companies. Thank you. And what I see is the same thing over and over again. As I go in, they will apologize for the code base. I mean, obviously, nobody ever calls in a consultant unless they have a problem which is so big that they can't solve it for themselves. But when they call me in, they will apologize for the code that they're showing me. They say, look, we know it shouldn't look like this. We know it's stiff. We know it's gnarly. We know things have been going wrong with it. This is not how we set out. We thought this time it was going to be different. And yet somehow it's got out of control. Does this sound familiar to you guys? Am I in the right room here? So I have a question here. If I was to come into your team, or if I was to come into your company, would you feel the need to apologize for your code or to introduce it so that I'm not too judgmental about it? Well, don't worry, because I worked on a project which is worse than anything that you've had. And I'm going to prove it to you. I'm not going to tell you who the client was, but I had come to this project when it was reasonably mature. We'd got about 2.5 million lines of code. It had started off in Fortran. It had been translated into Pascal, then into Delphi, then into Delphi.net, then into C#.net. And this whole thing was overseen by a professional geologist. So you can imagine how good it was. We had one method in one module that was a mere 32,000 lines long, and of course, nobody was going to touch it. But one of the characteristics of this is that, first of all, we had 4,500 listed bugs, and that was quite a lot. We also, velocity had slowed to a crawl, and my job was to try to understand what was going on. So as I went into the company, I started analyzing their repository. And I found that they were running a velocity of about 2%. That is, every time they did a feature development, for every line that was delivering feature, they had another 49, 50 lines that was bug splatting somewhere else in the code. Because what was happening here was each new feature development, it exposed latent defects elsewhere. And this was where their velocity had gone, because they were fighting technical debt that was attacking them from all sides. Excuse me. Now, I should have had more sense. I should have quit. But instead, I said, let's see if we can sort this code base out. So we did a quick calculation. We said, all right, which of these bugs are important to us? So we deleted the entire bug list, and we waited to see which ones came back. After 6 weeks, 4,500 of them had come back. OK, so we can't prioritize. We tried to work out what would happen if we switched over the entire team from feature development into bug fixing, just so that we could loosen the problem. We found out that we could get through most of the bugs if we did no feature development for 300 years. OK. So then we asked the next question. If we can't take these bugs out, then why were we putting them in? Could we avoid putting them in the first place? And now see if this matches your experience. We had this sense that writing software is just difficult. We had this sense that there was bugs just happened to us, that they were almost like they were floating around in the air, waiting to pounce as soon as our backs were turned. But that wasn't happening. What was really happening, in fact, that has only ever happened once in history. They wrote it down. It was in 1942. And this is incidentally why they were called bugs. It was a moth that flew in and got fritzed on the high-tension wires in the back of this computer. Apart from that, who would have thought it? The bugs were in our programs because we put them there. In fact, when we did the analysis, there were, to approximation, almost no bugs of omission. There was almost no points at which something was going wrong because we'd forgotten to do something. What was happening was things were going wrong because actually we were trying to do the right thing, but in doing that best practice, we were making matters worse. And that was a real revelation. Now, when we did the analysis, we found two really interesting things. The first one was that the bugs that we were fixing, when we actually got down to figuring out what was causing them, they followed a very small number of very repeatable anti-patterns. So that was the first thing. These were detectable. We could even detect them almost automatically. But the second thing that we found was that there were certain behaviors that were happening that were responsible for bugs. We knew that it was the process that we were doing which was creating these anti-pattern bugs. Now, armed with those two bits of information, it meant that a solution was in sight. And that was really exciting. So, let's play a game. You know how this game's played? If you don't know, you'll catch on real quick. It's a very simple game. Incidentally, what we did, after we saw this in that code base, we then started looking at a bunch of other code bases, and these patterns were absolutely repeatable. So, we asked 1,000 code bases. OK, you've got the answer ahead. We asked 1,000 code bases what were the causes of the bugs that we were finding, what we were trying to do when we put the bugs in. 1,000 code bases said 2% of them were down to null pointers. Would you have thought more or less? More? Yes. OK. Error checking. When you're looking for error responses from calls, getting that wrong, getting that processing wrong, was responsible for 4%. At number 3, any guesses? Sorry? No, that was number 6. Exceptions. It turned out that every time we threw an exception to try to get ourselves out of trouble, we made matters worse. Every exception caused downstream problems, but this was still only 6% of our bugs. At number 2, we had string typing. Now, I'll talk a little bit later about what string typing is, but this is when you use a native type to try to describe something. Like, you think it's a date, you want it to be a date, but you put it in a string, and then repeatedly you have to check that it's formatted the right way and deserialize it into the form that you want. This is string typing. There are lots of different ways of string typing, and they are all incredibly toxic. But that was still only responsible for 14% of our bugs. The number 1 cause of bugs. Any ideas? It was debugging. We were amazed when we saw this. Every time somebody tried to fix a bug, they would create the malfunction, they would show that it was going wrong, they'd do their testing, they'd do their red-green testing, but they would then make the light go green, they'd say, okay, the malfunction's not there anymore. But when they did that, other bugs started popping up. Typically, between 1.2 new bugs for every fix, sometimes up to 3, very rarely up to about 5. Every bug fix surfaced new bugs. And that just ran away. That's where our technical debt came from. That's where our problem came from. Now look, here's my thesis. If we can stop creating those bugs, we don't have to do that. So what I'm claiming here, and I'm hoping to make the case before the end of this talk, is that you can, because these follow standard recognizable patterns, you can avoid them. You can not do them. And if you do that, if you create your code to the higher standards, if you create your code with definitively 0 bugs in, this is not military standard or aviation standard code. This is faster and cheaper and better in every respect than knowingly doing it wrong. And this was the big discovery. You have a question? Yes. They were. I wasn't going to talk about this, but it's a good question, so I'll cover it. What we found in doing this analysis, we found that a bug is not a single self-contained thing. It's got an anatomy. There's the malfunction, and the malfunction is the way that you know that it's there. This is the thing when you're running the program, and then it doesn't work as you behave. But the malfunction is not the bug. The malfunction, in every sense, in every case, is traceable to a defect somewhere else. Now, the point is that that defect is creating that malfunction, but it's creating other malfunctions. And the process of suppressing that malfunction makes it harder to suppress the other ones, and then harder to fix the defect later on. I can't show you the theory of that in detail here. I haven't got time, but it's in the book. I'm here to sell a book, right? Okay. So, do you think that it would be difficult to write programs which are definitively bug-free? Who thinks that that's impractical? Okay. Then I want you to introduce you to this man, Taiichi Ohno. He was the chap at Toyota who created the Toyota production system in the 1940s and 1950s. He basically built a whole theory, a whole management theory about this, but it was founded on 2 principles. The first one was Kaizen. Kaizen is the idea that you have a small number of improvements which together create a lot of improvement. Now, this is something which, as software developers, we've very much taken to heart. It lies at the heart of agility. It lies at the heart of a lot of other practices. But for Ohno, that wasn't enough. He had a second principle, which was called poka-yoke. And what that means is, supposing you're assembling a car and you assemble it wrong, Well, whose fault is that? Is that the assembly worker? No, it's the designer's fault for having designed the car such that there was a right and the wrong way to assemble it. And their view was that if you are going to make a car and make sure that it's a reliable car, you cannot test quality in as it comes off the line. They wanted to take the car off the production line and into delivery without any inspection at all. And this was in contrast with the way the West and even Europe was making cars at the time. They inspected everything, and they did more damage to the cars through the inspection than if they'd left them alone. And it's why 1950s cars were rubbish. This man, Edwards Deming, was an American. He went and joined Ono, and he went back to the States. He went back to Michigan, and he took these ideas with him, where he was laughed out of the room until the 1990s. He said something very important. He said, you have to cease dependence on inspection to create quality. You cannot test quality in. You have to design it in. You cannot test quality in. If you're doing testing, you cannot rely on testing to establish your quality. And then later on, Tom and Mary Poppendijk, they've been in the business for 60 years. For the last 20 years, they've been talking about lean software development, which is pretty much Deming's ideas translated into software. And they're very strong ideas. All of these people are saying the same thing. If you care about quality, you cannot achieve the quality by testing. You have to achieve it by some other means. Since I talked about defects, I'll carry on with this idea. The way you get programs with no malfunctions is to create programs with no defects. And we can test for malfunctions, but not very well. We can't test for defects at all. So the only way we can make code with no defects is by a process something like the Ono's Poka-yoke. Does that make sense? Okay. So let's pause for a moment. While, if nothing else, I have a drink. Why is programming so hard? Sometimes we talk about it as a craft, sometimes we talk about it as engineering. James was just saying, is software engineering or is it not? Well, there's something different about software. And I think the difference is that software has this quality to it. It feels brittle, it feels delicate, it feels touchy. Now, I think there's a strong reason why this is true. It's because of the way a computer works. Inside, on the chip surface, it's executing a series of instructions, and at some point, it takes a decision, and it branches, and it follows one path, or it follows another path. And when it does that, it fundamentally changes the mode it's doing. It can change its character. It's almost schizophrenic. And what a computer does is it takes decisions like this, maybe 1 million times a second. There's a lot of cascading mode changes going on. And each of these decisions can change the character of the job that it's doing. Now, we can build machines with 1 million moving parts. Don't do it very often, it's incredibly complicated. But these decisions that the program is doing is not like the moving parts, because the moving parts stay connected. Even on the chip surface, this circuit is connected to that circuit always. The conrod is connected between the piston and the crank always. They never move. These decisions that the software is taking are more like failures. They're more like breakages in an engine than they are like moving parts in an engine. So imagine what it would be like to drive a car that was having 1 million failures a second. If you've ever owned a classic British sports car, you don't need to imagine it. But for everybody else, but other engineering disciplines don't do it this way. Other engineering disciplines, okay, before I move on, the effect of this is that when our code hits a disturbance, if there's something comes in from the outside which is upsetting its behavior, or if it gets into an internal state which is not exactly what we want it to be, the nature of the software is that that disturbance gets amplified. It gets bigger and bigger and bigger, like a Jenga blocks tumbling. And we know from other engineering disciplines from the last 5,000 years that this is no way to build a system. We already know this. So what do the other engineering disciplines do? They design things to be variation diminishing. They create stability. And when you build a system, programmers will say, we can't make it perfect. We can't get rid of every defect. But if you make a stable system, if you make a variation diminishing system, it doesn't have to be perfect to work perfectly. Because even if it goes off course, then it can get itself back on course again. When you're in the car and you hit a bump in the road, you'll feel it on the steering wheel, but the car will return to straight and level pretty much right away. If an aeroplane hits a pocket of air and gets knocked offline, it will come back to straight and level flight, even if the pilot's in the toilet when it happens. So, what I think we need to be doing is building software the way we build those systems. And those systems rely on a number of principles which are almost entirely absent from software. This is Taipei 101. This is a skyscraper in Taiwan, in the middle of Taipei City. Now, this is an earthquake zone. This is right on the ring of fire. The ground pretty much never stops moving. And so you can see that most of these buildings are pretty low down. You can't build any higher than that because the ground isn't stable. But look at this. Look how tall that is. How do they make that building stand up even though the ground is moving the whole time? Well, the answer is this. Right at the top of this building, they have this huge ball. My brother used to live in Taiwan, and he would go up there and tell everybody it was made of gold. It's not. But it is very, very heavy. It's supported by cables above, and then it's propped up on hydraulics underneath. It looks like this. And so what happens is when the ground moves and it pushes the building over, the ball wants to stay where it is, and so the ball pushes the building back upright. There's no electronics here, no computers. This is naturally self-stabilizing. This building can't fall down because it's got this thing stabilizing it. Now, this is the kind of self-stabilizing system that we should be building into our programs. There's another principle which we need to build in, which is called failsafety. Now, everybody has heard this word. Everybody thinks they understand what it is. But actually, there's something special about failsafety. What we just saw in the tower was a special machine, a special articulation. It was a moving part which was stabilizing it. But in the fail-safe system, you don't have that. The reason I've shown this picture is you have all seen train carriages sitting around on sidings. Has it ever occurred to you to wonder why they don't roll away? Well, it's because of the way train brakes work. Inside a carriage, obviously you've got trolleys carrying the wheels, and each trolley carries a brake system. It's got a piston which pushes brake shoes onto the wheels. Every axle, in fact, every pair of axles has one of these. Now, these pistons are connected together by a pipe that runs the whole length of the carriage. One end of it is stopped off, and the other end is connected to the locomotive. Now, in the locomotive, we've got a similar pipe running the length of the car. Again, the brakes are driven the same way, and there's a pump here with a valve. Now, this pump is driven by the engine, so you have to start the engine for the pump to work, whether it's an electric motor or a diesel motor. That powers the pump. And then the pump pressurizes this system, and the pressure releases the brakes. Now, under normal circumstances, that valve is open. This is called the dead man's handle. And so the pump's putting air in, the air's coming out of the handle. To make the train go forward, he puts his hand on the handle, and that raises the pressure. Now, if the motor's not going, if you haven't got power, nothing happens, so it's safe. But assuming the engine's going, it takes the brakes off, the train can move forwards. If he takes his hand off, if he has a heart attack and falls off backwards, if somebody in the carriage presses the emergency stop, the pressure comes out of the system, the brakes all come on. If there's a separation at this point and the pipe gets snapped, the pressure in this side fails, the pressure in that side fails, and all the brakes come on simultaneously on every axle in every carriage. No other action is needed. What's happening here is that this has a naturally safe state, which is braking. And because of the signaling system, being stuck is safe. But it has this naturally safe state, which we need to lift out of. We need to be active to lift it out of its safe state to make it do anything useful. But the moment we let go, the moment anything goes wrong, it falls back into its safe state. Now that is what fail-safety is. And loads of systems in the real world are designed to be naturally fail-safe. Car brakes are not. Just saying. So, what would this look like in code? We're talking about these as engineering ideas, but what would happen in actual code? These are the principles that we really ought to be looking at. We ought to be building our code such as to be fail-safe. We haven't got time to talk about it, but engineering systems use a lot of feedback. They have more power than they need, but then they tap it away so that they get a lot of control. So that's a feedback system. Nicholas Taleb talked about anti-fragility. This is systems who are able to draw strength. There's brittle systems where if they get impacted, they break. They were fragile systems, but anti-fragility is systems where if you impact them, they get stronger. And he had a lot of talk about that. Most important is this idea of self-stabilizing code. This is the kind of thing that we saw in that building. In 1968, Edgar Dijkstra wrote an article about self-stabilizing code, and he was claiming actually all code should be of this form. That was 1968, and it was doable back then, but nobody was listening to him. In 1984, Bertrand Meyer, in one of the Paris universities, I forget which one, created the language Eiffel. And the idea behind Eiffel was exactly the same thing. Eiffel is, in its syntax, self-stabilizing. And it's definitely a language worth looking at, even if you don't intend to use it. So what does this look like in code? We saw null pointers. Null pointers are a problem. Everybody hates them. But why are they a problem? What's the underlying defect that makes them so bad? This man is Tony Hoare. This man was responsible for all of that pain, single-handedly. Again, back in 1968, 1969, he was writing Algol, which was a very early structured language. He threw in null on a whim. He said it's going to be no hardship to implement. Well, about 10 years ago, he was in an interview, and he admitted that that was his billion-dollar mistake. And he apologized. But why is it such a big mistake? When we see a piece of code that looks like that, what we think is that this is describing a variable which exports an interface T, whatever that is. And so whatever we want to do with it, it's a T. It means that if we write something like that, then either Q is a T or has a T-like interface. And if it doesn't, it's implying something like that. But in fact, when we write that, it should mean something like that. We just create the declaration at that point. It should mean something like that, but it doesn't. It means something more like that. And the thing about this is that this is not a T. It doesn't have T's interface. It has a completely different interface, and it behaves in a completely different manner. And so every time we look at one of these things, we have got to... Sorry, my microphone's falling off. Every time we look at one of these things, we have got to check which of those things it is. Is it a T, or is it one of these peculiar pointer things? And you get languages like Rust, which wrap this up in a monad, like maybe, which is great. It means it forces you to check every time you use it. Yeah, that's brilliant. But here's the thing. What we really want, null has survived as long as it has because it's doing something useful for us. It's not working as well as we'd hope, but it is doing something for us. And what that is a refusal to answer. Sometimes we just don't have an answer, or sometimes we want to provide an answer which is fundamentally an error state. We need something like that. That is, we need a nullary object, something which contains no state and no identity, but something which nevertheless exports the whole of T's interface. This is a failsafe. If you build your system using nulls, then you can lift it out of that failsafe state by putting real values in there, but the moment you let go, it all falls back down to nulls, and they self-stabilize. And this is not new. That is also nullery. What we do with these exist because we've, say, divided by 0, and there is no number which is a correct answer. So we answer with something which is not a number. But we can compute with it. We don't have to stop there. We don't have to check whether it's unnormal until we've got way, way down, and we really need to know what the value is. We can continue to operate with these nulls and with these unnormals. Let me show you another example. This is not an example, this is a summary. You're going to get the slides, but this is basically a summary of what I've just said. Do you need me to read it out? No, you're perfectly capable of reading. You're all grown up. All right, here's the next principle. We want to protect the happy path. We need to understand what the logic of our code is. The code should be an argument in favor of its correctness. But remember that one of those points on our list was excessive error checking. So I want to show you a piece of code, and I hope that you're going to agree that this is representative of the kind of code that you see in the wild. You can see what this is purporting to do. It's reading a CSV file. I suspect that you probably can't see what format it expects the CSV file in or how it's parsing it. I mean, you know that it's returning a dictionary of some kind. But you can see there's an awful lot of logic here, which is not about reading CSV files. It's about hand-holding the machine. It's about babying the machine. Okay? It's worse than that. This is this whole function. Now, if there's a bug in there, if there's a bug either in the processing or in the error handling, it's pretty well camouflaged. You can't see it. You also can't test it, because all of these funny cases, most of this code is about error conditions that should never happen. So they're impossible to test unless you distort the system. This, would you agree that this is production type code? You've seen this, haven't you? But this code began like this. And even if you don't know the notations, like this is kind of a mapping operator, and we've brought parts of, we've brought interfaces into scope without having to repeat them. The point is that you can see the logic of this really simply. And so you're going to ask me, well, what about all of those funny cases? What if the file's not there? What if there's a line blank? What about all of those things that the other code was checking for? How does this handle this? It doesn't. The fail-safes handle it, because this is already imbued with enough intelligence to get itself back on track, to find a safe state, to find to be able to produce safe responses and get itself back on track when things get into trouble. It's the fail-safes that look after this. This is self-stabilizing code. This is the kind of code we need to write stably, to write reliably. So, let's summarize where we've got to. I started my career 40 years ago building aviation systems. And my first job, in fact, was to prove mathematically that a piece of code was going to run correctly. And I wouldn't wish that on anybody. It was hellish and truly not practical. But over the time, I've been in and out of safety critical systems an awful lot. And the more I've learned is I've found that those lessons from those systems translate directly into the kind of code we write at industrial scale. And it is true, it is reliable that if you do it right, it takes less time. There's considerable evidence coming out now that if you tame your technical debt at the point of source, you can get your velocity up by 10 times. And this is experimental evidence. This is not just me telling you this. This is not just my experience. I feel so strongly about this that I have written a book about it. This is the book. You can get it from there. A lot of the things that I've talked about here, that I've not been able to talk in detail, the justifications are in here. So it's well worth having a look. I mean, of course, I would say that, wouldn't I? I loved writing this. But I think there's something else to think about, and that is that even though you get an immediate economic benefit from writing code correctly, and I would suggest try it, just see how much smoother things become when you write clean, definitively clean code. But there's something else, and that is that reliability is the same thing as security. Every time you have a security breach, every time you have a data breach, it's been facilitated by a failure in reliability. If you can harden your systems, if you can make your systems inherently safe, inherently defect-free, then that will reduce your attack surface down to 0. And this matters because these days, bad security is a criminal matter. Companies get fined, directors get imprisoned for getting this wrong. So my strong feeling is, I mean, on Monday's keynote, he was talking about doing more with less. This kind of thing will allow you to do more with less, but it's also about the security. That is pretty much all I have. Any questions?